Welcome to the lesson on friction. In this video, we're going to talk about what friction is, how to calculate it, and how do we take it into account on flat horizontal surfaces and on surfaces that are at an incline. To get started, let's go to the reference table and let's write down the equation for friction. We have F fric for friction is less than or equal to, and we have this mu, which is the lowercase Greek letter. And you see down here to the lower left, we have our mu cat. I personally can't stand cats, but I'm a Leo and I love lions, so we're going to let this ferocious lion be our mu cat. And so we're going to pull a mu out of our mu cat. And the mu stands for the coefficient of friction. Be clear that that is not friction, that is the coefficient of friction. We'll talk more about that in a second. Finishing out the equation, it's mu times the normal force between the surface of contact and the object itself. Mu depends on the coefficient. You could look at this and say, all right, well, friction can either be static or kinetic. So the friction that exists between an object at rest and trying to get it moving versus the friction between a moving object and the surface itself, which is always less. It takes less force to keep an object moving than it does to get it started moving. So then we really don't deal at all with a less than circumstance. So you're just going to see us say equal to. We're interested in an amount of force to just break it free and start it moving or to keep it moving. Okay. We'll pull another mu from our mu cat times Fn. So if we were to solve for mu, you can see that one way you could look at mu is to say, oh, it's simply a ratio of the force of friction. We'll just use little f this time to Fn. So it looks like it's a ratio of the frictional force to the normal force. And while that may be true, the coefficient of friction really depends on the molecular interaction between the two surfaces in contact with each other. For example, if you take your rubber tires on your car versus dry pavement, that molecular interaction is different than the rubber and the tires of your car and, say, wet pavement or even on ice, for example. So because of that difference in molecular interaction, we have these different coefficients for various substances in contact with each other. That also depends on the frictional force and the normal force, and we'll get more into that in a second. We often are asked also, can the coefficient ever be greater than 1? And the answer to that is also yes. And I'm going to provide you with a supplement that shows you various coefficients between various surfaces in contact with each other. Be careful that you're not looking at a situation in which the surfaces are bonded, like there's glue or some kind of adhesive, because that's not the same. Right? These two surfaces need to be rubbing or moving against each other, relative to each other, in order to count it as friction and a coefficient of friction. Where did this equation come from? We always like to take a quick look at that. If we were to make a graph of the frictional force that we would plot on the y-axis and the normal force that we could plot on the x-axis, when we make that graph and we get a linear fit for that set of data, and of course what this indicates to us is that the frictional force is directly proportional to the normal force. Well, how do we get these two quantities to be equal to each other? We get them equal to each other by multiplying usually the x data by a proportionality constant. The proportionality constant always comes from the slope of the graph. And what we find is that that proportionality constant is the coefficient of friction. This allows us to take that step from being directly proportional, now saying, okay, now we're going to set these equal to each other. Well, we have to multiply the normal force by the proportionality constant, which is called the coefficient of friction. You also note that if you were to solve for mu here, again, same as what we've done above, that coefficient, the units, would be newtons divided by newtons. Newton's the unit of force, newton's the unit of normal force, frictional force that is, sorry. Newton's the unit of frictional force, newton's the unit of normal force. So this is one of the two quantities in which there are no units for that quantity. Two quantities in the course, and one of them is coefficient of friction, no units. So no penalty for not including units on your answer for coefficient of friction. Cannot stress to you enough, keep straight the difference between the force of friction, which is FF, or FS for static, FK for kinetic, and the coefficient of friction itself. Okay? All right, let's move on and take a look at applying friction in a couple of circumstances here. Let's start by looking at friction on flat surfaces. So if we have a diagram here, here's our object, there's the surface in contact. If we were to say that the object is moving to the right, and we'll qualify its motion to be constant velocity. If you were asked to draw a free body diagram for that, and this surface has friction, how would you do that? Well, everybody says, okay, the weight straight down, normal force straight up, perpendicular to the surface. We have some forward force, forward, and we have some friction, and because the object is moving, we would say that it's kinetic friction. Friction always opposes the direction of motion. Friction always opposes the motion of the object. Okay? All right, so now we set this up and we say, all right, let's start with Newton's second law. Sigma F equals ma. Is this object accelerating? The answer is no. It's moving at constant velocity. Okay? And we're going to start out by looking at the summation of forces perpendicular to the object. Okay? Now let's re-ask the question, is this object accelerating perpendicular to the surface? The answer is still no. What forces act perpendicular? We would say Fn is positive because it's up, minus mg because it's down, equals 0. So we can see that our normal force is equal to the weight of the object when these are the only two forces acting perpendicular to the object. Now let's also summate forces parallel to the surface of contact. Is the object accelerating parallel to the surface? The answer is again no. It's moving at constant velocity. So back to the statement we made earlier. What forces, what would your summation be here? F is in the direction of motion, so therefore it's positive. Fk is opposite the direction of motion, therefore it's negative. So F equals Fk, which is mu k Fn. So now we have the formula for friction applied here. And so F equals Fk equals mu k. And now we're going to take our value of the normal force. We're going to substitute it in this spot right here. So F equals Fk equals mu k mg. Okay? If we take a look at friction on an incline, let's go ahead and do that. Let's just draw an object that's tipped at an angle. It also is moving up the incline at constant velocity. We'll keep it simple for now. At some point, of course, we could have that accelerating. For now, constant velocity. What would be your free body diagram for this object? Of course, we have weight straight down, normal force perpendicular to the surface of contact. Okay, if you're having trouble with that, let's draw a surface here. There's the angle theta. Any other forces? Yes, we were told there's friction in this problem. So we have our kinetic friction acting down the incline opposite the motion of the object. Well, obviously, if it's moving up, we also have a force up the incline as well. Is that it? Well, that is, this would be your free body diagram. If this was an exam, this is what you would put. These are all the forces acting on the object. However, what we always do is we sketch in the components to not forget them. And a nice review from an earlier lesson, the perpendicular component mg cosine theta and the parallel component mg sine theta. Okay? All right. Once again, let's summate forces perpendicular to the incline. Okay. Is this object accelerating perpendicular to the incline? The answer is no. It's not accelerating down the, against the incline or up away from the incline. What would the summation be? Fn minus mg cosine theta equals 0. So our normal force is equal to mg cosine theta. More on that in a moment. Now we're going to also summate parallel. Erase that. Parallel to the incline. Is this object accelerating parallel to the incline? Again, the answer is no, because it's moving at constant velocity. What would our summation be? F in the direction of motion minus mg sine theta down the incline minus Fk equals 0. Well, F then would be equal to Fk plus mg sine theta. And now what we're going to do is substitute in the equation for friction. F equals, sorry about that, mu k Fn plus mg sine theta. And now once again we're going to take our value of the normal force and sub it in here and clean this up. Mu k mg cosine theta plus